Today, we're digging into a really clever solution for one of quantum computing's biggest headaches, and it all boils down to a super powerful idea: splitting the work.
And look, this isn't just theory anymore. Platforms like IBM Quantum and Amazon Bracket mean that you can actually get your hands on these incredible machines right now through the cloud.
The big catch, though, is that these early quantum computers are incredibly delicate. They're super sensitive to, well, pretty much everything around them. And that creates a ton of errors, what we call noise. Now, this noise creates a really frustrating bottleneck that's holding back progress. Think about it. Everybody wants to use the one or two machines that work the best, the ones with the least noise. So what happens? You get a huge line, a massive traffic jam. Today, we're going to see how some researchers are clearing that road. All right, let's get into the weeds of this quantum traffic jam. To really get it, you have to understand the era of quantum computing we're in right now. It's got a name: the NISQ era. So what's NISQ? It stands for Noisy Intermediate Scale Quantum. And you got to focus on that first word, noisy. That's the key. And because of all this noise, every time you try to run a job, you're fighting this constant battle between two things you really want. First up, you want fidelity. I mean, that's just a fancy word for accuracy. You need to know that the answer you get back is actually the right answer. High fidelity is the goal. But at the same time, you want high throughput. You want speed, right? You can't just be sitting around for days or weeks waiting for your results to come back. And that right there is the heart of the problem.
So this puts researchers in a really tough spot. It's this classic dilemma. Do you get in that super long line for the one single best machine, the one with low noise, so you can get a really accurate result? Or do you just grab whatever machine is free, a noisier one, get your answer back fast, but it's probably wrong? You can see how neither of those options is great. So it just begs the question, right? There's got to be a better way. Can we somehow get the best of both worlds? Can we get high accuracy and high speed?
All right, so let's get into the really cool part, the big idea behind this new approach. And it all starts by taking a closer look at how a really common type of quantum job works. It's called a variational algorithm.
See, these kinds of jobs, they don't just spit out the answer in one go. They're iterative, meaning they work in steps. They start out really broad, kind of exploring all the possibilities. And then slowly, iteration by iteration, they start to zero in on the best answer. The sculptor analogy is perfect here. You know, they'd start with a big sledgehammer just to knock off the huge chunks and get the rough shape of a statue. Then they pick up the fine chisel for the details. And that's where the light bulb moment happens. What if we split the job in the exact same way? We could use one of those noisy but easy to get machines for all that early, rough sledgehammer work. And then, only when we need to do the final, precise chisel work, that's when we switch over to that super busy, high-fidelity, low-noise machine.
Okay, so this isn't just an idea. It's been built into a real framework, and it's called QuSplit.
So think of QuickSplit as this incredibly smart traffic controller for quantum computers. You feed it a whole batch of jobs you need to run. It knows everything about all the available machines, which ones are noisy, which ones are clean. And then it uses this really powerful technique called a genetic algorithm to figure out the absolute perfect schedule for everything.
And the goal here isn't just about making one single job run better. It's about optimizing the entire workload. QuSplit is the one making the big decisions. Which jobs should we split? Where do we send the different pieces? How long should each stage run? It's all about finding that perfect, elusive balance between getting the right answers and getting them done fast. Okay, so that all sounds great in theory, but does it actually work? Well, the researchers put QuSplit to the test against two of the most common ways people are doing things right now. And the results? I mean, they speak for themselves. This chart shows it all. If you just wait for the best machine, sure, you get amazing accuracy, high fidelity, but your throughput is terrible because you're waiting forever. If you just use any machine that's free, the round-robin approach, yeah, you're fast, you get high throughput, but your results are full of errors. And then there's QuSplit, hitting that perfect sweet spot. It delivers both high fidelity and high throughput. It's the best of both worlds. But hey, anyone can make a nice-looking chart in a simulation, right? The real test is, does this work on actual hardware? So to prove this was for real, they ran the whole experiment on an actual machine, the IBM Strasbourg quantum computer.
And the results were, well, pretty stunning. Instead of taking a whopping 40 iterations on a single noisy machine to find the answer, the job-splitting method got there in just 15. I mean, think about that. That's a 62.5% speed up. That is a massive difference.
Okay, so let's just zoom out for a minute and think about what this really means for the future of quantum computing.
Here's the key takeaway. We can't just sit on our hands and wait for some magical, perfect, fault-tolerant quantum computer to show up. I mean, that could be years, maybe decades away. We need to be clever right now. And frameworks like QuiSplit are so important because they're like a bridge. They let us do real, useful, high-quality science on the imperfect machines that we have today.
What this research really proves is that with smart software, with clever ways of managing our resources, we can seriously speed things up and bring the whole promise of the quantum revolution a lot closer. And it just makes you wonder, right? What other brilliant, simple solutions like this are just waiting out there to be discovered?